because at the end of Okay, this is the good stuff, and I hope you're excited because at the end of this module, you will absolutely know the major components of both Kubernetes as a cluster and how it manages apps. So here's the plan. We'll start off with the view from 1,000 feet, yeah? Because it's usually a good idea to have an overall view of everything before we dive deeper. Anyway, once we've got that big picture, we'll really start diving in. And we'll start with the infrastructure bits first, like the control plane nodes and the workers. Well, then we'll switch back and we'll look at the bits of Kubernetes that we use to deploy and manage apps. And I guess, seeing as how pods are the most fundamental and atomic unit of scheduling on Kubernetes, we'll look at those first. Then we'll see how to expose apps on a network with Kubernetes services. And we'll look as well at how Kubernetes deployment let us do really cool things with our apps like scaling and rolling updates and even versioned rollbacks. And look, I know I haven't even started and I'm already throwing the buzzwords around, but don't worry, we will explain every one of them as we crack on with the course. Anyway, we'll finish up with a quick chat about what the heck the Kubernetes API is and the API server. And then we'll wrap the module up with a quick flyby recap that'll be a great test of how well you've grasped the concept so far. So don't skip that bit. Now, one last thing before we go. This is a getting started course, yeah? So we're not going to be covering everything Kubernetes can do. I mean, not even close. But we will absolutely cover more than you need to get on your feet and taking your first steps. You're really going to love it. So I tell you what. Grab a pen and paper, flip yourself into learning mode, and let's get our heads around what the big picture architecture stuff looks like. So at the highest level, Kubernetes is an orchestrator of microservices apps. And like we said a minute ago, microservices app is just jargon for an application that's made up of lots of small and independent services that work together to create a useful application. And that's fine. But what's this orchestrator buzzword? Well, I think an analogy works really well here. So, in the real world, a football team or a soccer team, depending on where you live in the world, well, it's made up of individuals, and each one has a different set of skills and a different role within the team. And I'm sure even if you're not a football fan, you appreciate that some players will sit back and defend, some push forward and attack, some are great at breaking up play, some are creative, and some are quick. You know the score. Oh, nice. The score. Anyway, look, the team's actually a bunch of individuals with different skills and abilities. Well, along comes the coach, and she or he gives everyone a position and a responsibility, basically organising everyone into a team. So we go from this absolute mess here to this beautiful formation. You know, something that looks like a team with a plan. But you know what? It doesn't stop there. The coach is also responsible for in-game decisions, so responding to real-time events. So imagine this player up here in the top left gets injured and maybe can't play on. Okay, nightmare, but it is the job of the coach to react and replace them with an appropriate teammate. As well as that though, what if this is like a must-win game and the scores are tied at 3-3 and there's only maybe 10 minutes left to play? Well, if it's a must-win game, a draw gets you nothing. So the coach might switch from 4 defenders at the back here and 3 strikers at the top to just 3 defenders and 4 attackers. Well, guess what? And I'm not kidding here. But microservices apps in the Kubernetes world are just like this. Seriously, stick with me. So we start out with an app made up of multiple services. Each is packaged as a container, yeah? And we're massively high level right now. But each one is different with a different job within the overall app. So we've got load balancers, web servers, logging, the whole picnic. And Kubernetes comes along a bit like the coach in the football analogy, and it organizes everything into a useful app. So things like on the right networks and port, the right credentials, you name it. And what we end up with is a useful application made up of lots of small specialized parts. And we call this, what Kubernetes is doing, orchestration. It's orchestrating all of these pieces to work together, kind of as a team. But Kubernetes also reacts to real-time events. So let's say one of the reporting instances up here fails and we drop from 3 to just 2. No sweat, it's the job of Kubernetes to notice this and spin up a new one, taking us back to 3. And as well, what if it's year-end and reporting is getting hammered like we said before? Well, you probably guessed it, Kubernetes spins up more reporting containers to handle the demand. Alright, magic, but pictures are easy. How do we actually make this happen? So we start out with an app. We package it up and give it to the Kubernetes cluster. The cluster is made up of one or more control plane nodes and a bunch of workers. The control plane is the brains of the cluster, so that does all this stuff like scheduling tasks, monitoring stuff and responding to events and all of that jazz. Then the workers are where we run our user and business apps. Now, we're in kindergarten right now. It really looks more like this, yeah? And we'll cover all of this later. But for now, I feel like that's enough of this. So that's our physical infrastructure stuff, a cluster of control plane nodes and worker nodes. But at the start, we also said something like we packaged the application and we gave it to the cluster. So to do that, we take the app code and we containerize it, which is just jargon for making it run as a container. But we take that and then we wrap it in a pod, detail to come later, yeah? But then if we want things like scaling and self-healing, we wrap that pod in a deployment. Head spinning stuff, I know, but don't worry, you're not supposed to understand it yet. I mean, if you do, brilliant. But if it is making your head hurt, good. Stick around because it's just early days and all I'm doing right now is seeding ideas for later. For now, right, I'm just going to say we define all of this in a Kubernetes YAML file, which is basically just a way to describe what the app should look like for Kubernetes. So things like which container image to use, which ports, what networks, how many replicas, all of that stuff in a file. Then we give the file to Kubernetes and Kubernetes makes it all happen. And as we're about to see, it is incredibly powerful. Well, that's like the, whatever I said before, I think 100,000 foot view. Should we start getting deeper? Heck yeah, let's do it. Right then, control plane nodes. Now, on the terminology front, we used to call these masters. However, Kubernetes now follows the guidelines of the Inclusive Naming Initiative and is removing any potentially harmful language from the project. So, if you see old documents or references to Kubernetes masters, they are talking about control plane nodes. Anyway, as it's control plane nodes that run the brains of Kubernetes, it is super important that they're always available. So, running multiple control plane nodes for high availability is most definitely a thing. In fact, you should never deploy Kubernetes to production without a highly available or HA control plane. Now then, on this, right, normal HA rules apply. So, pick an odd number and for goodness sake, stick them in different failure domains that are connected by fast, reliable networks. Like, come on, I mean, sticking them all in the same data center rack under the same dodgy aircon unit? Whew, that is an automatic nomination for a Darwin Award, and at the very least you should expect to lose your job. Now on the topic of how many control plane nodes for HA, for the most part, 3 is the magic number. 5 is an option if you're paranoid, but going more than 5, I don't know, that can just start to increase how long it takes for the cluster to reach consensus, which, if you're not familiar with consensus, think of being out in a group and deciding where to eat. If there's only 3 of you, it's easy, but if there's 23, you're probably spending half the night deciding. Well look, it's similar with control plane consensus and not ideal to have too many. So, 3 is the magic number for most people, 5 is good if you want a bit more resilience, and 1 is better than 2. Whoa, hang on a second. 1 is better than 2. Yeah, I should probably explain that. So this comes down to avoiding something called a split brain or a deadlock. So imagine a cluster with 4 control plane nodes, and if the network connecting them goes down like this, we've got what is called a split brain. Basically, all 4 know there used to be 4, but now the max that any of them can see is 2. And that's a problem, because if none of them can be sure that they've got a majority, then they all go into read-only mode. I mean, look, your apps that are running on the cluster, they're still going to work, but you won't be able to make updates. However, if you'd only had 3 masters, then this side here knows it's got a majority, so it elects a new leader and the cluster carries on at full throttle. This one over here obviously knows it does not have a majority. So 1's better than 2 because an odd number is always better than an even number. Now, I think I mentioned leaders as well. So despite the fact that HA control planes are a thing, Kubernetes operates an active-passive model where only one control plane node is making active changes to the cluster at any one time. We call that one the leader, and we call the others followers. And the followers proxy connections over to the leader so that the leader can make the actions, yeah? Well, if the leader goes down, they elect a new one. Now, look, if you're building your own cluster, you need 1 or more Linux machines to run your control plane. Now, a couple of things to mention. Those Linux machines can be pretty much anything, anywhere. Like, Kubernetes couldn't care less if they're bare metal physical servers in your on-prem data center or virtual instances in the public cloud. All it cares about is that it's a modern version of Linux and Kubernetes is cool. Now, the other thing to note is that every control plane node runs a bunch of smaller services that are responsible for individual control plane features, and every control plane node runs the full set of features, so any one of them can act as leader. Now, if you're building Kubernetes yourself, you get to choose the number and the size of your control plane nodes, but on a hosted Kubernetes platform, the control plane is hidden from you and your cloud provider manages all of that. But again, let me back up a second. Hosted Kubernetes. This is where your cloud provider runs Kubernetes for you as a service. So you basically get an API endpoint, but the mechanics of how everything is built and all the upgrades and the performance and the high availability and stuff, that's all handled by the cloud behind the scenes, like it's a service, yeah? However, of course, like all things in the cloud, it costs money. So you get a so-called production-grade cluster with pretty much 0 effort, but you pay a price for it. And for a lot of people, it is a great model. So AWS Elastic Kubernetes Service, Azure Kubernetes Service, and Google Kubernetes Engine, they are the big ones, but you know what? Loads of others exist. Now then, it's generally considered a good practice not to run user apps on control plane nodes. In fact, if you're consuming a hosted Kubernetes service, you've got no choice because you can't even see the control plane nodes. But generally speaking, right, and certainly in production, you should probably restrict your user apps to running on worker nodes and leave the control plane nodes to focus on the Kubernetes stuff. It's about lines of demarcation. Plus, you know what? It keeps designs clean and simple. Well, tell you what, let's have a look at some of the services that make up the control plane. Okay, first up is the API server, and this one's a biggie, right? So it is the gateway to the cluster. In fact, look, it's the only component of the control plane that we will ever interact directly with. So that means anytime we send commands to the cluster, yeah, we are sending them to the API server. And then anytime we receive a response, that comes from the API server. And you know what? The same goes for worker nodes and applications. If any of them need to communicate with anything on the control plane, they do it through the front door of the API server. In fact, you know what? Even other control plane services, they all talk to each other via the API server, so it's pretty important. Well, you know what, like all good things these days, it exposes a RESTful API over a secure port and it consumes JSON and YAML. And then in the case of users deploying and managing applications, we send it YAML files describing what we want, the API server authenticates, authorizes and validates the request, and assuming all's good, it instructs the other control plane features to deploy it and manage it. Okay, next up, the cluster store. This one's the only persistent component on the entire control plane, and it's where the config and the state of the cluster are kept, and that includes the config and state of all apps. Right now, it is based on the etcd NoSQL database, and it's automatically distributed across all control plane nodes, though You can swap it out for something else, or you can even run the etcd bits on dedicated nodes, but that's pretty advanced stuff. Anyway, look, it is super critical to cluster operations, and in large busy clusters, honestly, it's probably the first thing that's going to become a performance bottleneck for you. And look, that's no disrespect to etcd, it's just the fact that doing distributed databases at scale, it's hard. So if you expect your clusters to be large and busy, like lots of change, then you really should look at the performance of the cluster store. Oh, look, and of course, you've got to have things in place for backup and recovery and regularly test them. All right, what next? Oh, yeah, the controller manager. So this is like a controller of controllers, if you will. Like inside of this, we've got a bunch of smaller controllers that are each responsible for something different. So there's like a node controller in charge of nodes, a deployment controller in charge of deployments, an endpoints controller, a namespace controller. There's pretty much a controller for everything. Now, look, we're going to check it out in more detail in a second, but each of these runs as a reconciliation loop. So it's watching the bits of the cluster that it's responsible for, and it's looking for changes. The aim of the game being to make sure that the observed state of the cluster matches desired state. Okay, well, right now, all of those little individual controllers are managed by the overall controller manager. Okay, last but not least, we have got the scheduler. This watches the API server for new tasks, and it assigns them to nodes, though that is doing it a huge injustice because actually it's pretty complex and has to chew on a ton of things like affinity and anti-affinity, constraints, taints, resource management. There's quite a lot going on. But look, you know what? That's enough for now. The control plane nodes run the brains of Kubernetes. Commands and queries come into the API server here, usually from the kubectl command line tool. They get authenticated and authorized, and then, well, let's say it's a command to deploy a new application. Well, the desired state of the app gets written to the cluster store, and the scheduler farms the work out to worker nodes. Only it doesn't stop there. Once that's done, the various controllers sit in watch loops, observing the state of the cluster and making sure it matches what we've asked for. And that's the crux. Now, look, there's loads more detail and plenty of examples as we crack on with the course. Right now, though, let's take a quick look at worker nodes. Okay, well, straight away, we can see that workers are at least a little bit simpler than control plane nodes. So there's basically three worker components that we care about: the kubelet, the container runtime, and kube-proxy. First up, the kubelet. And let me be clear about this. The kubelet is the main Kubernetes agent that runs on every cluster node. And I'm talking about worker nodes and control plane nodes. And we might come back to that later, actually. Anyway, you can start with a Linux or a Windows machine, because worker nodes can be Linux or Windows. But as well, they can be physicals, VMs, cloud instances, you name it, right? All you do is install the kubelet, which basically registers the node with the cluster. So things like adding its CPU, RAM, and other resources to the overall cluster pool so that the scheduler can intelligently assign work to the kubelet or to the node. Now, speaking of work, and we'll get to this shortly, but work on a Kubernetes cluster comes in the form of pods. Detail to come, remember. But right now, just think of a pod as one or more containers packaged together in a single deployable unit. Okay, well, it's the job of the kubelet to constantly watch the API server for new pods that are assigned to it. When it sees one, it pulls the spec and runs the pod. But it also maintains a reporting channel back to the API server to keep the control plane in the loop. Okay, well, we said that Kubernetes runs pods and that pods are one or more containers, meaning if we strip everything away, it's all applications running in containers. Only Kubernetes and the kubelet don't actually know how to run containers. Like, they don't know how to pull image layers or even talk to the OS kernel to build and start containers. For all of that stuff, it needs a container runtime. Now, in the early days, Kubernetes baked in Docker as its container runtime. But then it made this whole layer pluggable with something called the Container Runtime Interface, or the CRI. Well, look, to cut a long story short, for the most part, this container runtime, the bit that's got all the smarts on how to start and stop containers and the likes, on most modern Kubernetes clusters, it is container D. But, like we just said, it's pluggable and there are tons of other runtimes out there. In fact, look, take this as a homework assignment. Grab a notepad or something, because I recommend you look up gvisor and kata containers. Again, okay, others definitely exist, but these are a couple that I think will give you a decent idea of some of the features and differences out there. Well, that all said, whichever container runtime you do choose to use, they take care of the low-level sort of start and stop container stuff, yeah? Magic. Well, the last piece of the puzzle is the kube-proxy. And this is kind of like the network brains of the node, yeah? So for one thing, it makes sure that every pod running gets an IP. And it is one IP per pod. So if you're running multi-container pods, so pods with multiple containers in them, all of those containers are going to share the pod's single IP. Meaning you're going to have to use ports and the likes if you need to reach individual containers in the same pod. But I'm getting ahead of myself. We'll come back to that later. Though, no, actually, you know what? Yeah, let's do this now. Let's go and get ahead of ourselves. So the kube-proxy also manages lightweight load balancing across all the pods behind a service. I'm definitely going to regret getting ahead of myself here. So a service, right, is a way of hiding multiple pods behind a single reliable IP address, a bit like a load balancer. So, I don't know, let's say we've got a bunch of web servers here all talking to a backend down here. Only we put this backend behind a service so that there's just a single IP address. Well, we configure the web service to talk to the service, and then the service balances traffic across all three pods behind it down here. Well, the kube-proxy plays a major role in this load balancing that goes on at the bottom. But look, you know what? I reckon that's workers. So the kubelet is the main Kubernetes agent on every node. So it registers nodes with a cluster, and then it watches the API server for new work assignments and reports back on their status. Fabulous. Well, sitting next to that is the container runtime that does all of the heavy lifting of building and starting containers. And then there's the kube-proxy doing all of the network magic. Good stuff. But there's actually something else. And this might blow your mind. I know it did with mine when I first saw it. And we'll talk about this in a bit more detail in the getting or installing Kubernetes section later. But some cloud services provide nodeless Kubernetes. So that is Kubernetes without any nodes. And if you're like I was, you'd be like, what? How is that going to work? And you'd be right. I mean, I have just spent the last few minutes telling you that nodes are where business apps run. Okay, well, a lot of cloud platforms these days already have a hosted container platform. So a service where you just run container workloads without having to spin up VM instances or whatever, yeah? And look, you know what? From a developer and an admin perspective, it can be pretty sweet. You literally forget all of the low-level infrastructure stuff and you just let your cloud provider service run your work. And of course, then you only pay for what you run. Well, some clouds offer that for Kubernetes. You just post your app configurations in Kubernetes YAML files to an API server endpoint, and the cloud just runs them. You don't need to know the machinery or the mechanics or any detail of how or what they are running on. But yeah, it most definitely can be brain-melting stuff. But if that is hurting your head, just put it on a shelf for now. We'll come back to it when we look at how to build Kubernetes. And you know what? I reckon that is the clustery or sort of infrastructure stuff done. Next up, we're going to flip our attention to the stuff that actually runs our applications. But I want to do a kind of half-time show first on something called desired state and the declarative model, because this stuff is absolutely vital to Kubernetes and all of this cloud-native microservices stuff we've been talking about. So here goes with a little bit of a half-time show. Right. Like I said, I want to stress the absolutely fundamental nature of two things in Kubernetes. Like, without these, Kubernetes is just nothing. So, I'm talking about the declarative model and the concept of desired state. So, first and foremost, Kubernetes operates on a declarative model. Yeah, I love it. Jargon, right? But all this means, at a high level, is that we give Kubernetes a config file that describes what we want. So, like what we want the cluster and our apps to look like, and we call this our desired state. Now then, it's important to understand these config files, or manifests as we sometimes call them, they're not long lists of commands that need to run in order to get us to a desired state. No. They are a description of what things should look like. Well, we post these to Kubernetes, and it's up to Kubernetes to do whatever it takes to get us to that desired state. And you know what, look, I hate jargon, so maybe a quick but slightly cheesy analogy, so stick with me. It's all a little bit like hiring a building contractor and saying, right, we want a new kitchen at the back of the house. We want it open plan to an eating area, hook it into some underfloor heating. We want a bunch of glass on a south-facing wall overlooking the garden. We want a door into the garage or garage, I don't know how you pronounce that. Let's have an island in the middle of the kitchen. Oh, and why not? We'll have a rooftop garden. And of course, look, I'm making this stuff up, right? But that is pretty high level, and it's describing what we want. It's our desired state. So what it is not doing is saying, okay, knock down this wall here and slap up a steel support beam. Dig a foundation, however deep, right, whatever. Build 30 courses of bricks on a double-skinned wall with, I don't know, pins every 18 inches or whatever. Use 25mm pipes for the underfloor heating, blah, 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 blah. It is not saying anything like that. It's just describing what we want. In fact, actually, long lists like knock this wall down, dig this hole or whatever, we call that the imperative model. Now, okay, look, of course, like all analogies, it only goes so far, but I think you get the point. You describe what you want the cluster or the app to look like, and Kubernetes does all of the work of choosing which worker nodes to run stuff on, pulling and verifying images, starting containers, building networks, protecting secrets, all of that jazz. We don't really have to care about it. We know what we want, we just don't want to have to care about how we get it. Now, this method of just describing desired state is called the declarative method. You're declaring what you want. And like I said a second ago, the method of providing long lists of commands and actions to perform, that is called the imperative method. And look, Kubernetes supports them both. It just strongly prefers the declarative method, and you'll see why soon. Well, look, to do all this declarative stuff, we post manifest files to the API server describing the desired state of our applications in the cluster. It's basically a record of intent, yeah? And that's good and all, only after things are up and running, we all know things can still go wrong, like things break or we have to change stuff. Only, of course, when that happens, it is totally possible for the actual observed state of the cluster to vary or drift from our desired state. Look, I don't know, maybe a node fails, or maybe we even intentionally change the desired state. The point is, anytime observed state diverges from desired state, Kubernetes gets like all, this isn't right, I must reconcile. And it goes to work until observed state is back in sync with desired state. So what you see is what you actually want. Now, look, as a quick example, let's say we've got a desired state that says we always want 3 instances of a web front-end pod. Okay, well, right now we've got 3 workers with 1 pod scheduled to each. And that's magic. We want 3 and we've got 3. So Kubernetes is all relaxed and chilling out. But then, what if, horror of all horrors, one of these workers goes down? Well, desired state still says 3 pods, please, but observed state says, only 2. And like I hinted at before, this is like torture for Kubernetes, because Kubernetes is obsessed about observed state matching desired state. So it leaps into action, fires up another pod on one of the 2 surviving workers, and as if by magic, observed state is back into sync with desired state, and Kubernetes can chillax again. And look, I totally get it if that sounds simple, but I'm telling you, it is outrageously powerful, and it is at the very core of how Kubernetes operates. So of course, make sure it sinks in. We never interact imperatively with Kubernetes, or we shouldn't, right? We give it declarative manifest files that describe how we want the cluster to look. These form the basis of the cluster's desired state, which gets persistently stored in the cluster store, and the work gets scheduled out to workers. And boom, desired state is both recorded and implemented. But yes, then in the background, the control plane's running all these controllers that are basically reconciliation loops, constantly checking the current observed state matches desired state. And when they match, it is all peace and bliss. When they don't match, though, wow, it is all hands on deck until they do. But, I mean, it's all Kubernetes hands on deck, right? The whole point is Kubernetes does this without having to involve us. And look, with that hopefully stored in your heads, let's go and look at the most fundamental unit of work in Kubernetes, the mighty pod. Right, in the VMware world, the atomic unit of deployment is the virtual machine. In the Docker world, it's the container, and in the Kubernetes world, it is the pod. Now, let's be clear about this. Yes, Kubernetes runs or it orchestrates containers, only those containers must always run inside of pods. So, thou canst not deploy a container directly onto Kubernetes. You see, a container without a pod in Kubernetes is a naked container, and Kubernetes has pretty strict views on nudity. Now, obviously, I'm kidding and maybe I'll edit that out. However, I thought it might help you remember. Now, look, you absolutely can run multiple containers inside a single pod, and in fact, you'll do this a lot as you increase your experience and skill. And look, I've got this course here that goes into all of that depth, so maybe take a note of that course or a screenshot or something like that for later. And yeah, look, I know, literally the longest name ever for a course. Don't ask. Anyway, look, what is a pod? Well, at a really high level, it's just a thin wrapper that Kubernetes insists every container needs. But more technically speaking, a pod is a shared execution environment. So I guess we'd better unpick that. An execution environment is basically a collection of things an app needs to run. So maybe an IP address and a network port, files from a file system, I don't know, a bit of shared memory. Well, look, every pod gets an execution environment. Or, look, every pod actually is an execution environment. And then the containers running in it share that environment. So let's say you've got two containers in a pod. Yeah, they're both going to share the pod's IP. So that means if you want to connect to them from the outside, well, because they're both on the same IP, you're going to have to map them to unique ports. Then as well though, inside the pods, if those two containers need to talk to each other, then they can use those same ports over the pod's local host interface. Well, obviously the same goes for volumes and anything else. All containers in the same pod share the same resources. Now, what this means in the real world is if you have a use case where two containers or two applications or parts of an application need to share memory or maybe the same volume, then whack them in the same pod. However, if they don't absolutely need to be tightly coupled like this, then stick them in separate pods and loosely couple them over the network. And look, you know what? For the most part, that's what you'll do. You'll loosely couple them in separate pods over the network. You see, running two containers in the same pod is really for specialist use cases. Now, let me just be extra crystal clear about something here. The unit of scaling in Kubernetes is the pod. So anytime you want to scale part of your app, you do that by adding and removing pods. So you do not scale by adding more of the same containers to an existing pod. Nuh-uh. Scale up, add pods. Scale down, remove pods. So look, multi-container pods are for two different but complementary containers that need to be intimate. And I reckon probably the most common example these days is a service mesh, which at a high level typically injects an additional container into every pod on a cluster. Then it's the job of this injected service mesh container to sit between the app container and the network, where it can encrypt and decrypt traffic coming in and out of the pod. Plus, it can expose telemetry and other cool network stuff. But the point is, it is all done by injecting an additional container into a regular application pod for the purposes of providing enhanced services. So, a complementary container that augments the main application container. Anyway, let's tie this back to the idea of pods being atomic. And again, there's two things I want you to know. First up, pod deployment is an atomic operation, so it's an all or nothing job. Now, by that, I mean that a pod only ever shows up and running and available for service once all of the containers inside it are up and running. Like, it's never going to show as ready and start accepting connections while only some of the containers are up. And the second thing, oh yeah, nearly forgot. The second thing is that all containers in a pod are always scheduled to the same cluster node. And that makes sense, right? Remember, we said it's a shared execution environment, so shared IP, shared volume, shared memory, all of that stuff, right? Well, it'd be a bit difficult if that was all distributed over multiple nodes. So yeah, scheduling a pod is an all or nothing atomic operation to a single node. Now, as well, pods are mortal. They're born, they live, and they die. And that's it. Like, there's no magical coming back to life or anything. And that's even true when we're deploying pods through higher level controllers like deployments that do self-healing. You see, in those cases, and I'm getting ahead of myself again, but the term self-healing is a little bit misleading. You see, the deployment controller spins up a new pod that's identical to the one that's died. So it's not the dead pod being brought back from the other side, it's a brand new pod that just happens to look, smell and feel identical to the one that failed. So, pods, they're atomic and they're mortal. I love the lingo. Now, for the most part, we deploy pods via some higher level controller like a deployment or a stateful set, because these are what bring the good stuff like scaling and self-healing and maybe ordered startup and persistent network IDs and stuff. And we'll cover some of these later, so don't stress. But it begs the question, if pods don't bring anything obviously valuable over and above what a standard container does, like we've just said they don't self-heal and they don't scale, then why do we bother with them? Like, why don't we just deploy containers? Well, yeah, that's a good question. No, I'm just kidding. Pods are really good. They let Kubernetes do a bunch of accounting and management stuff. Like, they're a great way to annotate and add labels and stuff with custom metadata that Kubernetes and other apps can use to add value. But also, they're a great way to apply policies and things like resource constraints and resource requirements. So, no, pods don't bring any of the blockbuster features like scaling and rolling updates, but they do allow Kubernetes to augment containers in a bunch of useful ways. And remember, okay, we're just covering the theory here. We've got plenty of exciting examples coming up. Anyway, before we do that, let's take a look at what Kubernetes service objects bring to the networking party. So, we've got applications, and we've said that in the Kubernetes world, they're going to be made up of containers running in pods. But we just learned that pods are mortal and can die, and that even if we bolster them with higher level controllers that replace them when they die, any new pods that arrive come with new IPs, which is obviously a bit challenging from a networking perspective. Only, you know what, it's not only when pods die, like if we scale an application up, all the new pods arrive with new IPs. Then, if we scale it down, we're shutting down pods with IPs that clients might be using. And it doesn't even stop there, because if we do like a rolling update or something, you know, like where we iterate through shutting down old pods and replacing them with new ones with a new version, well, it's an absolute ton of IP churn. So, the crux of the issue, we cannot rely on pod IPs. So, as an example, let's assume we've got some microservices app with a service that other parts of the app connect with. Pretty standard, right? But how's it going to work if you can't rely on these pod IPs? I mean, it's pretty inconvenient if the IPs change every time you push an update. And on the flip side, nobody wants to code intelligence into their apps to track stuff like IP churn. Well, playing Captain Obvious here, this is where Kubernetes service objects come to the rescue. So at the highest level here, let's say this is a much simplified view of an app. There's pods hosting a web front end needing to talk to a couple of other pods down here. Well, we slip a service object in front, and this is just an object in the Kubernetes API, just like a pod or a deployment. So we define it in a YAML manifest and we give that to the API server. But once it's created, and we'll see what it looks like later, but for now, it sits in front of the pods down here and provides a stable IP and a stable DNS name. Oh, as well, it load balances requests to the pods down here. Meaning, if one of the pods here dies and it gets replaced by another, that's fine. The service is watching and it updates its list of valid, healthy pods. But importantly, and I am stressing this right, it never changes this stable IP and DNS name. You see, part of the Kubernetes contract with the service is that once it's deployed, the IP and DNS name will never, ever change. Well, you probably guessed it, but the same goes if we scale the pods down here. All the new pods with the new IPs and the likes get added to the service's list of valid pods, and as if by magic, we're load balancing across 4 pods now. Then, if we rolling update the pods, the old ones get dropped from the service and the new ones get added, and it is all business as usual the entire time. And you know what? At a high level, that's the job of a service. It's a stable abstraction point for multiple pods, and it provides basic load balancing. Now then, the way that a pod belongs to a service or makes it into the list of pods the service will forward traffic to is by using labels. Now, I'm going to take a second just to pause here and give a worthy tribute to the role and value of labels, because let me tell you, labels are just the simplest and most powerful thing in Kubernetes. I mean, the power and flexibility they bring, it's truly something to behold. So labels, if you're listening, thank you for all that you do. Maybe a few respectful seconds of silence. No, I'm just kidding, and I'm pretty sure that sounded weird. But when you've done a thing or two with Kubernetes, trust me, you're going to have a moment where you're like, yeah, all right, I see why he did that. Anyway, look, let's move things on. Where were we? Okay, yeah, we've thrown some labels on here, and you'll do this all the time, right? Everything in Kubernetes gets labeled, but we can see the backend pods are labeled as prod, BEs for backend, and they're at version 1.3. And then up here on the service, see how it's looking for the exact same set of labels. Well, this is what ties them all together. In fact, look, if we had some other pod up here that was totally different, like nothing to do with our backend, but we labeled it the same, then the service is going to load balance traffic to that as well, which we obviously wouldn't want. But you see where I'm going, right? When the service is deciding which pods to load balance traffic to, it uses a label selector that says, I'm going to send traffic to all pods on the cluster that have these labels. Now, let's say we're going to update the application on the back end to, version 1.4. Well, one way to do that is to say, okay, stop looking for this particular label and just look for the other two. Then, as we add a new pod here, it's going to match the label selector and be load balanced on. And the same for this one here. And as these new ones come online and the old ones stick around, we're balancing across them all. So, of course, some connections are going to hit the new version and some the old. So you might not do it this way. I'm just showing you as an example. But sticking with this, right, maybe after a while you're confident with the new version and you decide to remove the old 1.3 versions. Well, you could just terminate those pods, yeah? But if that feels a bit risky, another way might be to add this label like this. And now all of a sudden, only the new pods match and the old ones, even though they still exist, they won't get any traffic. And I'd say, right, maybe an advantage of doing this way is that we can flick back easy enough by dropping that label again. As well though, and you know what, I always struggle to know where to draw the line in these getting started courses, but a couple of things that I will throw at you before we move on. Services only send traffic to healthy pods. So if you've got health checks configured and they're failing for a particular pod, no sweat. The service is clever enough, it'll drop it from the list and it won't send any traffic. Oh yeah, they can be used to configure session affinity. You can configure them to send traffic to endpoints outside of the cluster, and plenty more. So yeah, services, a cracking way to bring network stability to the turbulent and unstable world of pods. Right, yeah. Next up, let's see how deployments bring game changers like scaling, self-healing, and zero downtime rolling updates. Okay, we've got our infrastructure at the bottom, and we know that the smallest unit of work we can deploy is the pod, and that every pod is running one or more containers. But I think we threw it out there that we don't usually work directly with pods. I mean, on their own, they're not really that snazzy, like they don't self-heal, they don't scale, none of that good stuff. So, we normally deploy them via higher level controllers that do all of that good stuff. Now, Kubernetes supports a bunch of higher level controllers, and we'll be looking at deployments that are for stateless apps, and they do things like self-healing, scaling, rolling updates, and rollbacks. Stateful sets are similar, but these are for stateful apps, and they add things like guaranteed startup ordering and persistent network IDs. Then there's daemon sets, jobs, cron jobs, you name it, there's a bunch of them, and they're all for different use cases. But on the control plane backend, they're all implemented via controllers. So for us looking at deployments, there's a deployment controller running on the control plane that watches for deployment configurations that we post to the cluster. That's our desired state. Well, anytime it sees one, it implements it, and then it sits in a loop and makes sure that the observed state matches the desired state. It's a reconciliation loop. Well, yeah, the same goes for stateful sets and the rest. They all operate as reconciliation loops on the control plane. Anyway, deployments. As a quick example, we might use one to deploy an app with a desired state of, let's say, 4 replicas. So desired state is that we always want 4 instances of the app up and running. Well, we define that in a YAML file here and throw that at the API server. And then before you can say Kubernetes, there'll be 4 pods on the cluster running the app. But if a pod dies for whatever reason, the desired state's still 4, but observed state will have dropped to 3. And then the deployment controller, which is sitting there closely watching things, notices the discrepancy, declares like a DEFCON 1 or whatever, and it's all hands on deck until the situation is rectified. And like we said before, this all hands on deck is for Kubernetes. You and me as developers or IT people, we can sleep through it all. Now, behind the scenes, deployments work together with another controller called a replica set. And it's actually the job of the replica set to manage the number of replicas and the likes. And then the deployment effectively sits above the replica set and manages that. So look, we've got a bunch of nesting going on here. There's the app in the container, which is in the pod, which is managed by a replica set, which in turn is managed by a deployment, which, when I was first getting my head around all this stuff, it was kind of like inside my head. So if you don't understand it all right now, that's all good. I'm basically seeding the concept so that when you see it in action later on, you'll be like, right, now I get it. Anyway, look, a deployment object looks something like this. And for now, we only really care that it's asking for 5 replicas. And replicas means pods, yeah? But I suppose as well, while we're here, we want them all to be based on this image here, on this network port. That's our desired state. But another thing I like about this, right, is that it's self-documenting. You can version it, and it's great for repeatable deployments. So spec once, deploy many, which is like the gold standard, right? Plus, it's just really transparent and easy to look at and get your head around. And that can be massive for cross-team collaboration and maybe onboarding new hires as well. But there's more, right? This all makes rollouts and rollbacks game-changingly simple. And who doesn't want that? But look, I'm waffling, back on track. Just like pods and services, deployments are first-class REST objects in the Kubernetes API. So we define them in YAML files, and then we deploy them by throwing those manifests at the API server. Then, like we've said a bunch of times already, the desired state gets logged in the cluster store as a record of intent, and the scheduler issues work to the cluster nodes. Then in the background, there's a control loop, making sure observed state matches desired state. And I reckon that'll do for now. Deployments really are where it's at for stateless apps on Kubernetes. Other controllers exist for stateful apps and other use cases, But for deployments which we're looking at, they enable self-healing, scaling, versioning, rolling updates, concurrent releases, and simple version rollbacks. Have some of that. Oh, and we're only setting the scene here. We'll be getting our hands dirty pretty soon. However, time for one last thing before doing a recap. I've mentioned the Kubernetes API and the API server a few times, so I feel it's only right that I explain what I mean. Now then, and this is especially true for people from an ops background, but the concept of an API and an API server can be a bit confusing. So here goes with a quick overview. Kubernetes is lots of moving parts that work together to deliver the infrastructure and features to deploy and manage modern cloud-native applications. So far, we've mentioned pods, services, replica sets, and deployments. Pods provide a mechanism for running containers, replica sets and deployments bring self-healing, rolling updates, and a bunch more, and services let us expose stuff on various networks. Well, all of these are objects or resources in the Kubernetes API. So, pods are a resource, services and deployments are. In fact, pretty much everything in Kubernetes is a resource in the API, even nodes. In fact, think of the API as a catalogue of features with a definition of how each one works. So look, if you need to expose a pod on a network or to the internet, you pick and use a service object. If you need a stateful app component, that'll be a stateful set object. Now, each object or resource has a bunch of features and capabilities that are defined in the API, or the catalog, yeah? So we looked at this a little while ago. It's a definition of a deployment object. We said it's asking for 5 pods running the app in this image and it's listening on this port. Magic. Well, these fields are all properties of the Kubernetes deployment resource as defined in version 1 in the Apps API subgroup. Now, older versions of the API might not have supported all of these properties and future versions might support more. But the point is, the API contains the definition and feature set of every object or resource in Kubernetes. That means when we post this manifest here to the API server, it knows we're defining a deployment object in this version of the API, and it knows what all of these fields mean and how to build what we're asking for. Now, the Kubernetes API is massive and it is evolving all the time. Anyway, look, the API server is a service on the control plane that exposes the API over a secure RESTful endpoint, which I know is more jargon. So, in layperson's terms, the API server is just the way that we reach and communicate with the API. Like when I said before that we post a manifest to the API server, for the most part we use the Kubernetes command line tool called kubectl. That's going to be all configured to know where to find the API server and how to authenticate and all that goodness, right? Then, when we want to deploy new apps and the likes, we use kubectl to send manifests containing a new desired state to the API server. And then when things are all scheduled and running, we use kubectl again to query the API server for the state of objects. So, the API is where everything's defined. Pods, services, deployments, nodes, you name it, okay? They're all resources in the API. And then the API server is how we access and use the API. Okay, so it's a RESTful API over HTTPS, so it supports all the major HTTP verbs like post and get, yeah? But I guess again, all just fancy jargon for saying it's a web-native API that supports the common methods for making updates and querying state. As well though, it is versioned and split into multiple subgroups. Now I get it, this is pretty heavy going maybe, especially if you're new to APIs. But seriously, you're not expected to remember all this. Just try and grasp the concepts. So I guess to summarize, the Kubernetes API stores resource definitions such as pods and services. It's versioned and divided into subgroups, making it easier to find things and use them. And it's exposed as a REST interface over a secure HTTPS endpoint via the API server. And that might well be the most jargon-filled sentence I have ever spoken in my life. But you know what? The good news is that'll do for now. And I get it, it has been a lot of theory. But all we've got next is a quick recap and then we're on to the hands-on, I promise. So stick with me. Alright then, We started out by saying Kubernetes is all about running and orchestrating containerized apps. And we made the comparison to a football or a soccer team. You remember, yeah? We said football teams are actually a lot like modern cloud-native apps. So both have lots of individual specialized members that come together to form something useful. Then we got on to how Kubernetes works. We said that a Kubernetes cluster is made up of control plane nodes and worker nodes. The control plane nodes are the brains of Kubernetes, and the worker nodes are where we usually run our business apps. Control plane nodes have to be Linux, but workers, they can be a mix of Linux and Windows. Now, as the control plane is the brains of the cluster, it does need to be highly available. Also, under the hood, it's actually a bunch of small specialized services. First and foremost of those is the API server, which exposes the API. Jargon, jargon, jargon. But we said the API defines every possible Kubernetes object, and the API server is how we access it. There's also the cluster store, which is where the state of the cluster and apps is kept, and it is the only stateful component of the entire control plane, and we need to have plans to protect it and recover it from failures. As well as that, we mentioned the scheduler and a bunch of other controllers. So the scheduler does what it says on the tin, right? It balances work across cluster nodes. The controllers, though, these sit and watch the apps we deploy and make sure observed state matches desired state. Then there's worker nodes. This is where user or business apps usually run, and they comprise a kubelet, a container runtime, and a kube-proxy. The kubelet's responsible for cluster membership and does all the talking with the API server, so it watches the API for new work assignments and reports on workload status. The container runtime does all the heavy lifting of like starting and stopping containers, and then kube-proxy handles the networking. And I think we kind of said that's the major infrastructure bits. So then we flipped onto workload objects like pods, services, and deployments. The pod is the atomic unit of scheduling on Kubernetes, and in and of itself, look, it's not like the star of the show. I mean, yeah, it's important, but it's not where the blockbuster features are implemented. These tend to be implemented in higher level controllers. Speaking of which, we mentioned deployments that bring scaling, self-healing, rollout, and rollbacks. We said that services bring stable networking for pods, which by design are actually unreliable. I think we said things like scaling and self-healing and updates and even rollbacks. These all add and remove pods from the network, which can be a real pain for apps that want to use them. So we stick a service in front of them, and then as if by magic, we get a stable IP address and a stable DNS name that we can use to reliably access a dynamic set of pods behind them. And I reckon that's the theory, and hopefully at least some of it is settling in. But if it's not, that's fine. It is totally normal for new stuff like this to take a while to settle, especially if you're running this at 1.5 speed or whatever. But look, my point is, don't stress if you're feeling like you're drinking from a fire hose. We all feel like that at times.